The universe is vast and mysterious. It is a realm that stretches beyond our wildest imaginations, filled with wonders that we are only beginning to understand. It stretches out in all directions, filled with billions of galaxies, each containing billions of stars. These stars, in turn, host planets, some of which may harbor life. But where did it all come from? How did this grand tapestry of existence come into being? How did this incredible expanse of space, time, and matter come to be? These questions have fascinated humanity for centuries, driving us to look deeper into the cosmos. The answer, according to the prevailing scientific theory, is the Big Bang. This theory provides a framework for understanding the origins of everything we see around us. The Big Bang theory proposes that the universe originated from a state of extreme density and temperature. This initial state was unimaginably hot and dense. Imagine all the matter and energy in the universe compressed into a tiny point, smaller than an atom. This point contained everything that would eventually become the stars, planets, and galaxies. This point, called a singularity, is where our understanding of physics breaks down. The laws of physics as we know them cannot describe the conditions within this singularity. From this singularity, the universe expanded rapidly. This event, known as cosmic inflation, occurred in a fraction of a second, setting the stage for the universe's evolution. This wasn't an explosion in the traditional sense, with matter bursting outward into pre-existing space. Instead, it was the expansion of space itself, carrying matter along with it. Carrying matter along with it. This expansion created the space-time continuum that forms the fabric of our universe. This expansion continues to this day, as we observe galaxies moving away from each other. The further away a galaxy is, the faster it appears to be moving, a phenomenon known as Hubble's Law. The Big Bang theory is a powerful explanation for the origin and evolution of our universe. It provides a coherent narrative that links the past, present, and future of the cosmos. It's supported by a wealth of observational evidence, and it continues to be refined and tested by scientists around the world. Observations of the cosmic microwave background radiation, the distribution of galaxies, and the abundance of light elements all support the Big Bang theory. In the following sections, we'll explore the key components of this theory, including the role of dark matter and dark energy, the formation of the first stars and galaxies, and the ongoing expansion of the universe. We'll delve into the mysteries it has yet to solve, such as the nature of dark matter and dark energy and the ultimate fate of the universe. And we'll reflect on its profound implications for our understanding of the cosmos. The Big Bang theory not only explains where we come from, but also helps us ponder the future of the universe and our place within it. One of the key pieces of evidence supporting the Big Bang theory is the observation that the universe is expanding. This expansion is not just a simple movement but a grand cosmic ballet that has been unfolding for billions of years. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that would forever change our understanding of the cosmos. He observed that galaxies are moving away from us, and the farther away a galaxy is, the faster it's receding. This was a monumental finding because it provided the first concrete evidence that the universe is not static. This observation, now known as Hubble's Law, suggests that the universe is not static but is constantly expanding. Hubble's Law can be visualized as a relationship between the distance of galaxies and their speed of recession, painting a picture of a dynamic and ever-changing universe. It's like dots on the surface of an inflating balloon. As the balloon expands, the dots move farther apart. This analogy helps us grasp the concept of space itself stretching, carrying galaxies along with it. Similarly, as the universe expands, the galaxies within it move away from each other. This movement is not due to the galaxies traveling through space, but rather space itself expanding and increasing the distance between them. The expansion of the universe is a fundamental concept in cosmology. It underpins many of the theories and models that scientists use to understand the cosmos. It's a direct consequence of the Big Bang theory and has profound implications for our understanding of the universe's past, present, and future. The Big Bang theory posits that the universe began as an incredibly hot and dense point approximately 13.8 billion years ago. It tells us that the universe was once much smaller and denser than it is today, and it suggests that it will continue to expand, possibly forever. This ongoing expansion raises intriguing questions about the ultimate fate of the universe. One of the most fascinating aspects of this expansion is the role of dark energy. Dark energy is a mysterious force that is driving the accelerated expansion of the universe. Scientists are still trying to understand its nature and how it influences the cosmos. Another piece of evidence supporting the Big Bang theory is the cosmic microwave background radiation. This faint glow which fills the universe is the afterglow of the Big Bang and provides a snapshot of the early universe. As we look to the future, the continued study of the universe's expansion will help us unlock more secrets of the cosmos. Whether the universe will expand forever, eventually slow down, or even collapse back on itself, remains one of the most profound questions in cosmology. Our quest to understand the universe's expansion is a testament to human curiosity and our desire to explore the unknown. Each discovery brings us one step closer to comprehending the vast and intricate tapestry of the cosmos. The Big Bang theory describes the evolution of the universe from a tiny fraction of a second after the initial singularity. In these earliest moments, the universe was an incredibly hot and dense soup of fundamental particles and energy. Temperatures were so high that even atoms couldn't form. As the universe expanded, it cooled. This cooling allowed for the formation of the first protons and neutrons, the building blocks of atomic nuclei. This period, known as Big Bang nucleosynthesis, lasted for just a few minutes, but had a profound impact on the composition of the universe. During Big Bang nucleosynthesis, protons and neutrons combined to form the nuclei of light elements, primarily hydrogen and helium. This process is responsible for the abundance of these elements in the universe today. It's a remarkable testament to the power of the Big Bang theory that it can explain the observed ratios of these elements with such accuracy. Section 4. Cosmic inflation, expanding at warp speed. The concept of cosmic inflation is one of the most fascinating and mind-bending ideas in modern cosmology. It suggests that the universe underwent a period of extremely rapid expansion in its earliest moments, growing exponentially in a fraction of a second. While the Big Bang theory successfully explains many observed features of the universe, there are some puzzles it initially struggled to address. For instance, the Big Bang theory could not fully explain why the universe appears so uniform and isotropic on large scales. This uniformity is a significant puzzle because, according to the standard Big Bang model, different regions of the universe should have evolved independently and thus should exhibit more variation. One such puzzle is the remarkable uniformity of the universe on large scales. When we observe the universe, we see that it looks the same in every direction, a property known as isotropy. This uniformity extends to the distribution of galaxies and the cosmic microwave background radiation, which is the afterglow of the Big Bang. Observations show that the cosmic microwave background radiation, a faint afterglow of the Big Bang, has almost the same temperature in all directions. This uniform temperature is surprising because, in the standard Big Bang model, different regions of the early universe wouldn't have had enough time to come into thermal equilibrium with each other. This means that there should be more temperature variations than we actually observe. This uniformity is surprising because, in the standard Big Bang model, different regions of the early universe wouldn't have had enough time to come into thermal equilibrium. Thermal equilibrium is a state where different regions have the same temperature because they have exchanged energy. In the early universe, regions that are now far apart would have been too distant from each other to exchange energy and reach the same temperature. To address this and other puzzles, physicists proposed a period of exponential expansion in the very early universe, known as cosmic inflation. This theory was first put forward in the early 1980s by physicist Alan Guth. According to this theory, a tiny fraction of a second after the Big Bang, the universe expanded exponentially, growing from a subatomic size to a macroscopic size in an incredibly short amount of time. During cosmic inflation, the universe expanded at an extraordinary rate, much faster than the speed of light. This rapid expansion would have stretched out any initial irregularities, making the universe appear smooth and uniform on large scales. The idea of inflation helps to explain why the universe looks the same in every direction and why the cosmic microwave background radiation is so uniform. This rapid expansion smoothed out any initial irregularities and ensured that the universe was remarkably uniform on large scales. The inflationary period would have ironed out any wrinkles in the fabric of space-time, leading to the large-scale uniformity we observe today. This smoothing effect is one of the key reasons why the theory of cosmic inflation is so compelling. While still a theory, cosmic inflation is supported by a growing body of observational evidence. Measurements of the cosmic microwave background radiation, the distribution of galaxies, and other cosmological observations all provide support for the idea of inflation. As our observational techniques improve, we continue to find more evidence that supports this fascinating and revolutionary theory. Section 5, From Energy to Matter, the building blocks of our universe. As the universe continued to expand and cool, a remarkable transformation took place. Energy began to condense into matter. This process, governed by Einstein's famous equation E equals mc squared, is a fundamental principle in physics. In the early universe, energy was abundant, and particles were constantly colliding and annihilating each other. As the universe cooled, the energy of these collisions decreased, and eventually it became low enough for particles to form without immediately being destroyed. This marked the beginning of the matter-dominated era of the universe. The first particles to form were quarks and leptons, the fundamental building blocks of matter. As the universe cooled further, quarks combined to form protons and neutrons, which eventually combined with electrons to form the first atoms.